Hello students, welcome to the physics class of vector analysis which comes under paper 1 mechanics of your semester 1. This is N. Chandana, assistant professor of physics from Government Degree College, Khartaba. Let us have a quick recap on the previous classes we have taken. Around 3 classes I have taken on vector analysis so far. So what all we have learned, let us have a quick recap on the previous class. Scalar and vector fields with examples we have taken. Polar and axial vectors we have learned, and partial differentiation of vectors we have done. We have learned del vector differential operator, I dou by dou x plus j dou by dou y plus k dou by dou z. We have learned the gradient of a scalar field, which transforms a given scalar field into a vector function by using gradient, that is del of phi over del of psi, where phi and psi are any type of scalar fields we can take. In divergence of a vector field and its physical significance also we have learned. Whether the divergence is positive, what happens to the density, that means that it gets decreased and it behaves as a source. The point behaves as a source. And when the divergence is negative, the point behaves as a sink, and where the density gradually increases. Okay, that means all the things gets converged at that point in the sink. While for the source, all the lines of force, they get diverged at that particular point. Now we come for line integral and curl of a vector field we have learned, that is del cross A bar. For the divergence we have learned del dot A bar, where A bar is the vector field, then del dot E is called divergence, while curl is meant to be del cross A. Now let us go for today's topics. They are right here. First of all, let us learn today again line integral. What is line integral, students? I have taught you in the previous class. It is integration of a vector along a curve. Integration of a vector along a curve is called line integral, right? It's called line integral. So for example, let me give an example. If A bar represents the force acting on a particle moving along a curve, force acting on a particle which is moving along a curve from P to Q. If I suppose, if I have a curve P, Q, then A bar represents the force acting on the particle which is making the particle to move from P to Q. Okay, then line integral P to Q A dot dl, where dl is the length element on the curve. It gives the total work done by the force during the motion of the particle over the path PQ. Okay, gives the work done in moving the particle from P to Q. Okay, this is called line integral. This is called line integral. So this is the significance of line integral. Line integral means the vector integrating a vector along a curve. Okay, that is line integral. Okay, now let us go for a few more integrals. They are surface and volume integrals. Okay, what is a surface integral? So let us consider a surface here. So now let me draw a surface first. Now let us consider this is surface integral. We have three types of integrals, students: line integral, surface integral, and volume integral. Now I am going for surface integral. Now let us consider a simple surfaces in a vector field bounded by a curve. Okay, let me take a simple surfaces in a vector field. So let me take a simple surfaces in a vector field bounded by a curve. Now consider a small element here, ds. This is the small element ds. ds. Small infinitesimal element ds. Okay, this surface element of area ds can be represented by area vector ds bar. If n bar be a unit positive vector in the direction of ds, then we can take it as n cap. Okay, n cap. Unit positive vector outward the surface, which represents the normal to the surface ds bar. Then how can I write the direction of ds? How can I represent that? ds is equal to ds bar is equal to n cap into ds. ds is the magnitude and n cap is the direction. Now let us consider a bar be a vector at middle of the element ds here. Let us consider a bar be a vector at the middle of the element ds. Now what's happening now? Let A makes an angle theta with n cap. Let us consider this is angle theta between n cap and a bar. So what's happening we'll see. Now the scalar product a dot ds bar. What does it give? A bar dot n cap into ds, right? So that is a ds cos theta. It is a ds cos theta. Okay, because we know that the dot product of any two vectors gives the modulus of a, modulus of ds, and then angle between the two vectors, that is a and ds. Because this ds vector is represented by direction n cap, that is outward to this, outward, that is normal to the surface area ds. Now the total flux of the vector field across the entire surface area S is given by surface integral a bar dot ds bar equal to surface integral a cos theta into ds, a ds cos theta, right? A bar dot ds bar is equal to a ds cos theta. So this is called surface integral of a vector, surface integral of a vector on this surface. So the surface integral of a bar, this surface is closed by a curve, can be given by double integral is a dot ds. So students, line integral we have single integral, line integral a dot dl. Let me erase these things. Now I'll show you. Line integral is a single integral along one dimension. It is along the line or the curve. Surface integral is double integral a dot ds. That is a surface, that is a plane, either xy or yz or zx. This is either x or y or z. This is line integral, this is surface integral. Now next let us see volume integral. The third one is volume integral. So what is volume integral? Let us learn what is volume integral. Now consider a closed surface in space enclosing a volume. Again, we consider a closed surface S in space enclosing a volume V. Let A be a vector point function at any point in a small element. Now I take a volume here, volume element dV. In previous case, I have taken a surface element ds. Now because I am considering a closed surface in a particular volume, closing a volume V, I will take a small volume element, that is dV. Okay, this is the element. If A be a vector point function at a point in a small element of volume dV. Now here I'll take A be a vector element in this volume V. Now the integration triple integral V A dot dv. Triple integral B. A dot dv gives you volume integral. Volume integral of the vector function, of the vector field. Okay, enclosed in this volume. Volume integral of vector A bar over the surface enclosing the volume V. Okay, this is triple integral. Triple integral, that is x, y, z. This is dx, dy, dz. Volume is 3 dimensions. It has dx, dy, and dz. So we have learned one surface line integral, integral A dot dl to surface integral, double integral S A dot ds. Then third, volume integral, learn triple integral V A dot dv. So we have line integral, surface integral, and volume integral. 3 types of integrals. Now let us relate these 3 integrals and by using 3 theorems. So we have 3 theorems here. They are named after the scientist who has given this, who have stated these theorems. Okay. So these theorems, what they will do, they will relate. Okay, these theorems give a relation between these integrals, like volume to surface or surface to volume or volume to line. So these 3 theorems are very important for your examination purpose also. So let us learn first Stokes theorem. Okay, so let us learn first Stokes theorem. First theorem, Stokes theorem. What does it Stokes theorem do? It relates the line integral to the surface integral. It relates, first point is this theorem relates line to surface integral. Okay, or surface to line integral. What does this theorem state? Is the line integral of a vector field A bar along a closed curve C. The line integral of a vector field A bar, the line integral of a vector field A bar along a closed curve C. Closed means this one. Closed curve C is equal to surface integral of curl of vector A bar taken over the surface S surrounded by the closed curve. Okay, surrounded by the closed curve means we are relating line integral to the surface integral here. You have to remember this statement. What is the statement? The line integral of vector field A bar along a closed curve C is equal to the surface integral of curl of a vector field along the surface enclosed by curve C. It's so simple. I'll explain you this with some diagrams here. See, listen to me. Now, I will write the theorem here so that you won't forget here. So this is line integral of vector A bar along the curve C equal to surface integral of curl of vector A bar along the surface S enclosing by the curve C. Okay, so this is the theorem. You have to remember this. Now let me prove this. How do you prove this Stokes theorem? This is LHS and this is RHS if I suppose. This is left hand side and this is right hand side. RHS. What does he say? He is consider a surface S enclosed in a vector field E. Now I consider a surface yes. enclosing a vector field A. Okay. Now the boundary of the S is closed curve. If I take a closed curve, the boundary of the surface as closed curve. This is a closed curve that gives you a surface here. It gives you a surface S. So what is the closed curve here? Let me take it as PQR is the closed curve. Now my closed curve is, consider a surface S enclosed by a curve, closed curve PQR, okay, which is enclosing the vector field A bar. You write these 3 points first. We are considering it. Closed curve is PQR, vector field is A bar inside the surface. Okay. Now the line integral A around the curve PQR. Now let us see the line integral A bar of A bar around the curve PQR. See, this is in anti-clockwise direction, right? PQR. So the line integral of A bar along the PQR is line integral A dot dr. Now let us consider that we have to prove that this is equal to curl of surface integral of curl of ds. Okay, curl of A dot ds. So now let us consider this surface to be parts of made into small surfaces, infinitesimal surfaces like this. Okay. Now since the vector field is anti-clockwise, so each of this surface of surface elements ds of surface area ds should also have the direction in this way, right? In anti-clockwise direction. The direction of each of these surface elements ds. Now what happens? As we know, the line integral of A around the boundary of the area you have to calculate, right? That's what, no, this is line integral of A around the boundary, the entire surface. Now I'll consider each and every element. Let us consider each and every element. For each and every element, what is the direction of the vector rotation? It is anti-clockwise, right? Anti-clockwise. Now I'll take this particular surface. If I take this particular surface, my direction is this way, this way, this way, and this way. Okay. I'll consider this 6, 9. Okay. Now see here. Now similarly for this surface ds, I have this way, this way, this way, and this way. For this plane, this way, this way, this way, and this way. See here, one for this surface, the vector's direction is this way, field direction. For this surface, the vector direction is this way. These two will cancel. These two will get cancelled out. So I have 0 here. Next I have, sorry. Okay. Now next I have, this one will get cancelled out. Oof. Okay, one side will get cancelled out. Then again, I have the other two sides. This one got cancelled out. This one got cancelled out. Again, for this surface and this surface, for this surface this would be downward, and for this surface this would be upward. Again, this will be cancelled out. This will be cancelled out. And similarly, this will be cancelled out. This will be cancelled out. In entire way, everything will be cancelled out, and finally, only my boundary curve will be remaining here. Okay, I'll considering the curl A. Hence, the entire curve will be remaining. So, my line integral will be del cross A bar. Now, let us consider as considered unit surfaces of ds elements, which are infinite elements on this entire surfaces closed by the curve PQR along the curve C. Now, what's happening now? Now we are taking curl of each of these elements ds. Okay, so each of these elements. Now I consider this element. I'll take the curl. So since this is an anti-clockwise direction or counterclockwise, what has happening? This way I'll have. Okay. Next, if I consider this element, this surface, how do the direction will be 1, 2, 3, 4. Okay. Now this element, this surface, 1, 2, 3, 4, because this is anti-clockwise direction or counterclockwise direction. We are taking the curl of the vector A bar along this ds surface, along this ds, all equal elements. I'm taking all the ds. See here, now I'll consider this element here. This way, this way, this way, and this way. Now for this surface element, how it would be? This way, this way, this way, and this way. Now this would be cancelled because this is in this direction and this vector is in this direction. So the resultant will be here 0, here 0. Similarly here 0, here 0, again here 0, here 0, 0, 0. In this way entirely the vector integration curl of this surface element will be 0. Curl of this element will be this element. Entire things will be 0. And all the things will get cancelled out, and finally I'll remain with my surface S, my only surface S, which is enclosed by curve C, that is PQR. Okay, that is equal to curl of line integral of A dot dr equal to surface integral of curl of ds. Okay, so this is my theorem. So we have proved that this is equal to RHS, right? So now we have taken for single element ds bar, we have considered del cross A for each and every element of this surface. Okay, then finally we have arrived at curve, that is the entire curve, that is line integral of curve along this vector. Okay, the vector. That's the reason the Stokes theorem is proved. Okay, so line integral of A dot dr along the closed curve C enclosing a surface S is equal to surface integral of curl of A of the surface S enclosed by the curve C. Okay, so this is Stokes theorem. Okay, so in this way we have learned line integral, surface integral, volume integral, and Stokes theorem today. Okay, students. So let us learn Green's and Gauss theorem, Gauss divergence theorem tomorrow. Okay. So that is summary, a brief summary. Well, let us see. First we have line integral. We have surface integral, volume integrals, and Gauss divergence theorem, and then Green's theorem and Stokes theorem. Let us see Gauss divergence and Stokes Green's in the next class. So we have learned line integral, surface integral, volume integral, and Stokes theorem. And problems also we have to see along with Gauss divergence and Green's theorem in the next class. Okay, students. Thank you so much for your patience listening.